Let's take a look at what a limit is. Limits are incredibly important for calculus. So to start out, I'm going to give you a very strange graph and ask you to find out what y is approaching as x gets close to some number. And then we'll talk about how that relates to limits. So as our x value gets very close to -4, where are we on the graph? So this is where we have an x value of -4. And what is our y value at this point? It looks like as the x value gets very close to -4, coming close to -4 from the left or the right, the y value is approaching -4. So that's what y approaches. As x gets close to -3 on the function, so here we are on the function getting an x value close to -3, what is your y value approaching? Looks like -3. As x approaches -2, -2 on the function is here and here. So if we're coming in from the left-hand side, say -2.2, -2.1, it looks like our y value is getting closer to -2. As we approach from the right-hand side, -1.9, -1.99, getting closer and closer to -2, it looks like the y value is approaching 2. So y is approaching -2, and it's approaching 2. As we get close to 0, where are we on the function? We're up here. Looks like our y value is approaching 2. And you might say it is 2. That's okay. We can also say it approaches 2. As we get an x value approaching 2, what is the y value approaching? Looks like 2 again. As we approach 3, this is where we have two possibilities. Coming in from the left, getting closer and closer to 3 along this graph, looks like we're approaching 0. Coming along this graph, getting close to 3 from something bigger, 3.2, 3.1, 3.01, 3.001, looks like the y value is approaching -1. So two answers for that, -1 or 0. As we approach 5, the y value is approaching -1. So we'll just do that again, take another look at that before we talk about the limit. So we're saying as your x value gets close to a number, and we get ourselves onto the graph to see what number we're approaching. As we approach -4, this is where we are on the function. The y value seems to be approaching -4. As we get close to 5, this is where we are on the function. Because we're always saying, what is the function value? And why are we talking about the function value? Because that's the y value. Now, how does this relate to the limit? Here are your answers for the limit. So it looks like the limit and what y approaches is the same thing, except in two situations. This one and this one. So the limit is the exact same thing as what y approaches, except when it approaches more than one answer. So our definition of a limit, a unique value, meaning we're not allowed to have more than one answer. It's what the y value approaches, so the limit is the same as what the y approaches, as x is getting close to a number. The way we write that, our new notation, is the limit. Here's our answer for the limit. It's a unique answer. It's what the y value, which is what f of x is, approaches, as x approaches some number. So just some new notation for you. We're saying the limit, x is approaching a, what's the value of y, and the answer goes over here. So let's try some. We're asking for the limit of the function as x gets close to -5. So when we're the x value close to -5, we're on the function there. What is the y value? I would say the y value is 1 for that. As the x gets close to -3, where are we on the function? And what is the y value approaching? I'd say the y is approaching 3 for that. X approaches -2. Oh, this is one of those interesting ones. We can approach -2 from the left-hand side or from the right-hand side. As we approach -2 from the left, -2.2, -2.1, getting closer and closer to -2, it looks like our y value is getting close to 4. But if we come from this side to the right of -2, -1.8, -1.9, -1.99, our y value is getting closer to 6. And what happens when there's two answers? That's when we say it does not exist. And why was that? It's because the limit had to be a unique value. So as we were getting closer to -2, we had one answer from this side, one answer from that side, and that's just not allowed. Now, let's talk about why that's not allowed. So the idea of a limit is that if we limit our x values to being very, very close to -3, can we equally limit our y values to being close to something? And the answer is yes. As you make this smaller and smaller with x, can we narrow that down to get closer and closer to some number? And the answer is yes for -3, and what we're approaching is 3. If we limit our x values to being very, very close to -2, can we also limit the y values? And the answer is no. You cannot make that very, very small as you make this very small. And that's why that limit does not exist. And that's where the idea of the word limit comes from. Trying to limit the y values as you limit your x values. Let's keep going. As x gets very close to -1, what is happening on the function? It looks like the y values are approaching 5. As x gets very close to 0, what's happening with the function? Looks like the y is approaching 4. As x approaches 2, this is an interesting one that we're going to have to spend some time on. As x gets very close to 2, did we say equal to 2? No, we said approach 2. So we don't actually care what's happening at the value of 2. We just want to get very, very close to 2. We can go from the left. We can go from the right. As we get close to 2, our y value is approaching 2. So what about this point? That point does not matter because we are not letting x equal 2. So we don't actually care what's happening right here. So you might even imagine putting a pencil down right here and then don't look under the pencil. So you don't care what's happening at 2, you care what's happening as you get close to 2. And as we get close to 2, the y value is getting closer and closer to 2. Let's approach -infinity. I'm going to get rid of some of this so we can see what we're doing. X getting closer to -infinity, that's way out there. What's your graph doing? The graph looks like it's heading in this direction. So what y value is that? As your x gets bigger in the negative direction, your y is doing the same thing. So we're approaching -infinity. What's happening as x approaches infinity? We're coming way out here, and we just have to make an educated guess of what's happening here, but it looks like we're approaching 0. So the limit again, unique value that y approaches as x gets to close to some number. Okay, how to do this when we don't have a graph? Well, one thing we could do is draw a graph and just see what happens. So y equals x squared, we know that's a parabola. As x gets close to 2, what y value is that? You'd figure it out by putting the 2 in, wouldn't you? So what you're doing is you're saying, as I get close to 2, I'm putting in a value very close to 2. My answer should be close to 4, and that's the limit. So essentially, we're just plugging in the limit and evaluating it. So this one, 5 times 3, 15. So this looks really straightforward. Again, all we're doing is saying, as x gets close to this value of 2, what's the y value getting close to up here? And then it gets harder, of course. As x approaches 2, let's plug in that limit. I'd get 4 minus 4, so I'm getting 0 on the top. 2 minus 0 on the bottom. Now, 0 over 0 is known as an indeterminate answer, meaning we have not yet determined the answer. This answer is not 0, it's not 1, it's not undefined. We just don't know what it is yet. So we're going to do some good math and change the way this looks. X squared minus 4, it's a difference of squares. Let's factor it. Oh, look at this. We can reduce that. That becomes much more simple. Plug in your limit. Cool. So that answer is 4. If you're wondering what's happening with the graph, x plus 2 is this graph, except there's a hole at 2, isn't there? So at 2, there's actually a hole in the graph. And we're asking ourselves, what's happening here as x gets very close to 2? So the answer, it's approaching 4, even though we have a point of discontinuity there. So that's one of the things that limits are really useful for doing, finding out what's happening when you've got holes in your graph. Okay, let's try this one. Plug in 2. I'm going to get 2 cubed minus 8. And on the bottom, 2 minus 2. Oh no, 0 over 0 again. So I think of 0 over 0 as a warning sign. It warns me that I need to keep going. I need to do something else. Difference of cubes. I hope you remember how to factor this. We take the cube root of each one of these. That would give us x minus 2. And then we said square that term, square that one, multiply them together and change the sign. All right, what can we do now? We can reduce those. That gives us a much simpler expression. Plug in the 2. We're going to get 4. 2 times 2 is 4, plus another 4, answer of 12. Let's try some more. Limit as x approaches 0. So put 0 in for x. Looking dangerous. 2 cubed is 8. Minus 8. 0 in the bottom. There's our 0 over 0 again. Feels like we might be getting a lot of those. What could we do with this? Luckily, we've just studied Pascal's triangle, haven't we? So how do you cube something? Do you remember? 1, 2, 1, 1, 3, 3, 1 are the coefficients. So expanding 2 plus x cubed, we'd write 1, 3, 3, 1. There's our 1, 3, 3, 1. And then we've got x cubed, 2 to the 0, x squared, 2 to the 1, x, 2 squared, 2 cubed. So that's using Pascal's triangle to expand this. And then please remember to put the minus 8 in. You've got to be really quite careful with this. Often we do a whole lot of work with Pascal's triangle. We're so proud of ourselves that we forget there's the minus 8. That minus 8 is quite important because when you expand this, 3 times 2, 6x squared, 3 times 2 squared, 12x, we'll get an 8 and a minus 8. And if you'd forgotten that, you wouldn't be able to go any further. So we'll get rid of those. And then we've got a common factor of x. So we can take an x out of everyone. So we take an x out of there, and an x out of here, and an x out of there, and an x out of there. Simplifies to x squared, 6x, and 12. Now plug in your limit. As x approaches 0, we get 0, 6 times 0, and the answer is 12. Isn't this marvelous? You get to use all kinds of wonderful math skills to work on limits. Just delightful, I say. All right, approaching 3. 1/3 minus 1/3. You might have an idea where this is heading. 3 minus 3. Yep, 0 over 0 again. So 0 over 0, indeterminate, have not yet determined what the answer is, do some good math. What did we say we did with fractions? We wanted to multiply by the common denominator, so denominator of 3, denominator of x, denominator of 1, so we're going to multiply everything by 3x. How does that help? When we multiply 3x by 1/3, we'll be left with x. When we multiply 3x by 1 over x, we'll be left with 3, and leave the bottom factored. So instead of multiplying this out, we just said it's x minus 3 times 3x. Why did we do that? Look at that. Beautiful. Now, keep in mind, when you reduce this, x minus 3 divided by x minus 3 is 1. We're not leaving nothing on the top. So there's our new limit, much simpler than it was before. Plug in the 3, and there's your 1 over 9. So, summarize what we've just done. When you're evaluating a limit, put the number in. If you get a number, you can just stop. Your answer can be 2, 5, 7. If you get an indeterminate form, which I'm calling a warning sign, such as 0 over 0, you have to keep going. Simplify the expression, change the way it looks, make it look different. And here are some of the ideas of what we did. We did some factoring, we did some expanding, we did some multiplying by a common denominator. So essentially, when you get a warning sign, it tells you you're not done. Do some good math. So reach into your bag of tricks. What have we learned that will help us change the way the expression looks? Okay, be kind to yourself today. This is new. It's very different. It's going to take a while to get comfortable with. Work on 1 to 6. Do the best you can. Some of them, they might stump you, and that's okay. Have fun.